We start recording. Wonderful. Okay. It's a great pleasure to welcome everybody to this One World Fractal meeting, hosted by Bristol this time. And the first speaker is Károly Simon from Budapest, and he's going to be telling us about some unusual separation conditions for hyperbolic IFSs. Thank you very much.
Thank you, Hannah. And thank you for the invitation to present this talk. First of all, because I would like to talk about unusual separation conditions for hyperbolic IFS, so I would like to start with hyperbolic IFS. What is hyperbolic IFS? They are something which I try to draw on this figure. So we are given an M is 3 on the figure, and we have M mapping. So the alphabet, A like alphabet, is 1 to M, and we are given a compact interval. This compact interval is this interval that you see over here, and we say that F like this is a C2 smooth hyperbolic IFS on this interval X, like this one. If the following two condition holds, we can find a little bit bigger open set like this V, as you see over here, such that F sends this V into itself, and Fi for every I, and Fi also sends X into itself, and the derivative is uniformly separated from 0 and 1. And once we will use this, that so it means that there is a bound, B like bound, Bi like bound on the derivative, and this is smaller than 1. So this is, you see here is, and then what is the attractor? The attractor is what remains after infinitely many iterations. So first of all, we consider the first cylinders like this xi. So this is I, and the first cylinder by F1 is this x1, and by F2 is this x. Pardon? And the third cylinder is this. So these are level 1 cylinders. These are level 1 cylinders, and then the attractor is the unique compact set for which this unique non-empty set for which this holds. But I prefer the other characterization, namely what we do it is that we consider the cylinders. These are the first cylinders, and similarly we consider the n cylinders, where this thing, what you see over here, simply means this composition. We will use this shorthand notation several times. This is just the compositions, and xi is the corresponding n cylinder corresponding to this index. So we take the union of all n cylinders, and this union will be a nested set for higher n. The union will be smaller and smaller, and when you take the intersection, then it is the attractor. So this is the attractor, and the Hausdorff dimension of the attractor. I believe that on this seminar, everybody knows the Hausdorff dimension. For those who do not know, I don't believe in, but nevertheless, this is the dimension. Now, since we work with not with self-similar mapping, so we will need something which extends the notion of similarity dimension, and for that we need the topological pressure. So what is the topological pressure? Actually, if you consider this definition of the Hausdorff dimension, then we consider here coverings. And if you take the covering like this, so if you take this covering, the covering with the n cylinders, so this yellow corresponds to this yellow, then in the definition, this sum, this gray sum, corresponds to this sum, and the topological pressure is just the exponential growth rate of this sum. So this is the topological pressure, and it is continuous, and it takes a positive value at 0, and at infinity, it will be at positive infinity, the value will be negative infinity. So it has a unique 0 or the pressure has a unit 0, and this is always an upper bound on the host of dimension of the attractor. We denote it in this way, and we always write SF. SF is the root of the pressure function, which is the most natural guess for the dimension of the attractor. In this talk, we always assume that we consider small hyperbolic systems, which means that this root of the pressure, which is the upper bound of the dimension, is smaller than 1. You can guarantee that it holds if bk, you see what was bk. Bk was here, upper bound on the derivative. If this sum of bk is smaller than 1, you can immediately get that it implies that this inequality holds. Yes. So we define a metric on the symbolic space. The symbolic space is the set of infinite sequences, one-side infinite sequences above the alphabet. The alphabet was this. Here is the alphabet A, and then this is the symbolic sequence. And we define the most natural metric where I and J are infinite sequences, and we take the common prefix of I and J, and then corresponding to that, we consider the cylinder. So this is the cylinder which corresponds to I by J, and we consider its length. And the length of the cylinder is the distance between I and J. We define the natural projection in the very usual way. I believe that this seminar, everybody knows that this is the natural way of labeling the elements of the attractor. So this is just labeling the elements of the attractor. It actually, by sends the symbolic space to lambda. So actually, I should have written here lambda. Okay. And then sigma I, as usual, is just the left shift on the symbolic space. And then I will consider many times ergodic measures on sigma. And then it is a consequence of a theorem of Daijun Feng and Hu from 2009 that you can get the host of dimension by this kind of variational formula. You get it as a maximum of invariant measure, but the supremum of ergodic measures. Okay. And then what is the entropy and the Lyapunov exponent? I believe everybody knows that when you want to compute the entropy, then you take a mu-typical element of the symbolic space. This is the first n. So I immediately write, I try if I can. So I is from sigma, and then I n is equal to I1, and so on, I n. Assuming that I was I1, I2, and so this is an infinite sequence. Okay, so you take this cylinder on the symbolic space, you compute its measure, and the exponential growth rate of the measure is the negative of the entropy. Similarly, you take a typical J, and you consider the corresponding n cylinder, and its length, you consider the length, and the exponential growth rate leads you to the Lyapunov exponent. Then in some more intuitive way to write it down, and we will write SF mu for entropy over Lyapunov exponent. This is the best guess for the host of dimension of the push-forward measure of mu. So our measure on the symbolic space is going to be mu. So mu is on sigma, and mu is always pi star mu, which is on the attractor. Okay. And then it is over there. So host of dimension, this is an upper bound on the host of dimension of the measure. If there is open set condition, then the host of dimension of the attractor is this SF. SF was defined somewhere here, the root of the pressure, and the host of dimension of the measure is this entropy over Lyapunov exponent if you have open set condition. And in the self-similar case, if you have exponential separation condition, then you have the same conclusion. I am moving fast because I believe that most people know perfectly this. Now we are getting to more interesting things. So this F is a C2 smooth hyperbolic iterated function system on this compact interval, and sigma is the symbolic space, and then P is the natural projection. We may assume that X, the compact interval, is 0, 1 doesn't matter. Now here we define a partition of sigma, because we focus on iterated function systems with overlap. You see, this first cylinder, X3, intersect this first cylinder, X2. So we are focusing the case when there is overlap. If there is no overlap, that the so-called strong separation property holds, then the class for every I from the symbolic space, the class of this partition consists of I itself. But if you have this kind of situation, which you can see here, you have heavy overlaps, then one particular point, which is in this case Pi, may have lots of pre-images. And then it gives you a partition of the symbolic space. Yes. And then for a probability vector Q, this infinite product measure is denoted by mu Q, and we call Bernoulli measure its push forward measure. So if you take the push forward, which is this mu, I forgot to write here Q, I should have written here Q, but nevertheless, the push forward of mu Q is this nu F Q. Okay. And it is easy to see, and it is actually in our book for the self-similar case, but otherwise it's and in many other places that if you consider this partition, so this partition, then this is a Lebesgue partition on the symbolic space, not only a partition but a Lebesgue partition. So we can use Rocklin's theorem, which implies that for every ergodic measure, there is a full measure subset such that whenever you take an element of this subset, then you have conditional measures. So this mu, psi, I are the conditional measures, such that this almost like Fubini theorem-like thing holds. So this is the well-known Rocklin's theorem, and we can disintegrate the measure because this partition is a Lebesgue partition. And just keep in mind that we always assume that SF is smaller than 1, because otherwise Daijun Feng knows a counterexample to those things that I am going to tell you. So this is assumed. It's important. So we are, as I told you, after 14 minutes, I could get to the unusual separation conditions, at least the first 3. Pardon?
No, 再看这透的。
Okay, so as is the first 3, there will be 4 altogether. So no dimension drop condition simply means that nu is supposed to be, just as previously mentioned, nu is the push forward measure. Nu is the push forward measure of like this, a push forward measure of a ergodic measure. So this is nu, and it is no dimension drop condition if it satisfies this. We mentioned that the dimension is always smaller than equal to this, but when it happens that is equal to, then no dimension condition. Now, almost unique coding condition is when for almost every element of sigma, you see this partition psi consists of only, you see that this happens, what is here, not for all I, but for almost all I. This is almost unique condition, and weak almost unique condition is more tricky. It is trickier, so I need to draw a picture. Imagine that this is somehow sigma. Okay, this is sigma, and the projection to the interval x is pi. And, oh, I'm sorry, it is not visible. Maybe it is visible now. Okay, so the projection is pi. And then weak almost unique condition holds if you can find a full measure subset. This is the full measure subset sigma prime. So it is a set of full measure, a full measure subset, so that if you restrict it to the full measure set, then this is injective. So it is one-to-one when it is restricted, but it may happen that, for example, you have a point here I, and then on this this is let me say psi I basically here. This is psi I, and it can happen that you have some j which is in sigma, but not within this sigma prime. So it was sigma prime. I like to show this sigma prime. Okay. So this is a little bit complicated condition. This is much better condition, but unfortunately this one is going to be more important. At least I believe that it's more important. So I try to keep it on. Let me say, oh my God, it's this. And here is a theorem. So if you have this C2 smooth hyperbolic IFS, and for a quasi-Bernoulli measure, what we have, it is no dimensional drop condition is equivalent with this weak almost unique condition, and they are even equivalent. So we have quasi-Bernoulli measure. I believe everybody knows what is quasi-Bernoulli, but for those who do not know the definition, this is quasi-Bernoulli. So here is quasi-Bernoulli measure. It contains or Bernoulli measure, and then and these people are equivalent. So we proved it with István Kolozsvári for the very easy the Bernoulli case, and then for more general case, it follows from Dae-Jun Feng's paper. I think corollary 4.7. This is what it gives, and the other equivalence is easy. It comes easier. So this is the more difficult one, and this is the reason that we know it only for, but not quasi-Bernoulli. I just sent an email to Dae-Jun before this talk, and whether it holds for all, and this is what we can say, that this is true for quasi Bernoulli, but that is for that. This is an equivalent condition, so this weak almost unique condition is equivalent to the no dimension drop condition, at least for these measures. And then why is that true? I just like to show just like to give some orientation why it could be true. There was a paper of this earlier mentioned Feng paper, which is somewhere here, and then Balázs Bárány and Antti Käinmäki somehow in this paper they proved something like this, where H was expressed originally with some conditional entropy, but Balázs Bárány and Antti Käinmäki wrote down that this is equivalent if you express H in this way, where you see this measure, this conditional measure appeared on this slide. So this was this conditional measure. And then you have no dimension drop because this is what you expect, entropy divided by Lyapunov exponent. So you have no dimension drop if you subtract 0. But in order to arrange that H is 0, because this is an integral and the measure is never bigger, this is probability measure never bigger than 1, in order to arrange that this is 0, it means that this person needs to be 0 always. This needs to be 0 always. It means that this person needs to be equal to 1. And this is the reason for what appears here, that actually the no dimension drop condition, because this person needs to be 1 for almost all I, this person needs to be 1. It basically means from this it is possible to conclude that this this measure which you have, this MIPC measure. So this is the measure, the conditional measure on this slice, on the partition. This measure needs to be a Dirac measure. So this measure is a Dirac measure. Is it clear to everyone? So this is a Dirac measure, this three things, no dimension to condition. If this is a Dirac measure, so I draw it differently. I do, this is, let me say I now, here, this is I, in the symbolic space. And then the measure mu I C is the conditional measure which lives on this slice here. And then it can happen that there are many points like these. There are many other points on the slides. These are, let me say, J. And then if J is there, it means that pi J is equal to pi I. It can happen that there are many. So this is a big set. So this set, what I write here, can be a big set in cardinality. It can be an uncountable set. But from the point of measure, the measure of this set, the measure of this set is a Dirac measure. And that is equivalent to the no dimension drop. And this is if and only if. And I have very, very little time left. So I would like to speak about one more condition, which we call ADA. And then this ADA condition is the following. We have the same setup, and we say that ADA holds if this G, for every epsilon, maybe I forgot to write every epsilon. So imagine that there is every epsilon. So for every positive epsilon, the set, which set? Where is that? This set has a positive, full measure. This subset has full measure, and this simply means that this is the collection of those i's for which if you go to level n, so you go to level n, and this is I, this is pi, and then you go to level n. You consider I, the first n coordinates of I, and then you consider the distance between I and pi j such that I is different. So I restricted to the first n coordinate and j restricted to first n coordinate different. And then the smallest distance which can appear in between i's and j's, so the smallest possible distance between with the first n cylinder different, this is the distance, and this distance is compared to the length of the n cylinder, which corresponds to I. So we compare it, and then it should be exponentially large. And here I presented a reformulation. We call it ADA because it's exponential distance from the enemy, and this shows a better way why it is exponential distance from the enemy. But I have just a few minutes, so I will skip this. This is for every epsilon, this set needs to have, so that it says basically that this distance is always bigger than C2 times e to the power negative epsilon n. So this is a sufficiently large distance. This is what we have there. And then, unfortunately, I don't really have time for that. But if you take this full measure set, when these limits exist, and then you pick an I from this G epsilon, this was G epsilon, and the intersection with this, and delta n is basically as big as that the length of the corresponding n cylinder, just a little bit smaller, as you see. Then the lower local dimension is almost entropy over Lyapunov exponent, smaller than that, just about this epsilon. but we are talking about this epsilon, which always appears. And then I just like to mention some consequences. If we have ada, then for this, it's easy to see that the local dimension exists. If you have ada, then at almost every point, the local dimension exists, and it is what it should be. And that's why if you have ada, then you have no dimension drop. And then Adams-Spivak proved that actually ada is equivalent to this condition. Let me explain you what this condition is briefly, because I have very small time. At many points, almost every point, if you have ada, then at almost every point, this pi is invertible. And if you restrict yourself to this set, what I show you, and you take the inverse of pi, so you take pi minus 1, then this condition means that pi minus 1 is held there for every alpha from this interval. Yes. And then another thing which may be important, that if we have so if you have so-called translated condition, but I unfortunately don't have time to speak about, then F lambda satisfies ada for almost all parameters. And this was proved for the simple case when you have manually measured by István and myself, and then Balázs Bárány extended it to ergodic measure, even extended it to much further. And then it's not difficult to see that open set condition implies ada, but the reverse implication doesn't hold. This means that ada is a more general condition than open set condition, and it gives nice things. For example, the local dimension is what it has to be. Thank you very much for your attention.